All right, so this week we're going to have two lectures which are more fun than mathematical modeling and mapping, which will be focused on multidimensional visualization, including 2D and 3D. So today we're going to go through 2D visualization using Python, including pseudo color plots, contours, and how to gridding on maps. All right, so in the last lecture, we went through basic data wrangling, including merging data frames in Pandas. And also we used a new library called GeoPandas in order to map data onto a global map. And we use example as the COVID-19 cases. And GeoPandas is one way known as the geospatial data analysis, but that's not the only way. And some of you already had trouble installing it, and that's price to pay because these are open sourced software, so there's not much support, and you have to figure out yourself. All right, so in this lecture, you will learn how to generate a grid mesh, especially in two-dimensional grid mesh, and 2D pseudo color plots, contours, and also Python tricks on two-dimensional visualization using Matplotlib and Basemap. All right, so if you still remember that we talked about one-dimensional NumPy arrays and also very briefly on two-dimensional arrays, and then we moved on to pandas. Now we're coming back to two-dimensional arrays. So if you remember that the function np.array, which generates from a list to a two-dimensional array. So if you do np.array with these lists, and then you actually got a two-dimensional array. So print out the array itself, and print out shape and size, and you get a 2D array this way. And the shape has 3 rows and 5 columns and 15 elements in total. So if you look at the NumPy array in this way, and this is the name of the NumPy array called np2d. And these are the elements. I have 15 elements at the moment. And these are the row index starting from 0 to 2. And that's the column index starting from 0 to 4. There's total 5 arrays, 5 columns in this example. Right. So two-dimensional arrays, they basically have 2 axes, right? One is the column axis, which is the column index going in the horizontal direction, and the row index going in the vertical direction. So as long as you know the indices of the element, and you can get that element. And you can regard this as a two-dimensional grid. So every data point is fixed on a grid based on the index in this way. Right, so three-dimensional is the same thing. You're adding one more dimension, layered like two-dimensional arrays. So let's take a look at how to convert those numbers into a color plot. So the two-dimensional array looks quite straightforward in this way. I have 15 elements, but what does that tell you, right? At least my eyes are not so sensitive to the numbers. I see a bunch of numbers, but they don't really make sense to me yet. So for two-dimensional visualization, one good way to do is color your data based on the values, right? So how are we gonna do it? So remember that this is my row index, this is my column index, so I have a grid. So I have, each data point is on the grid based on the index. So if I pick a color bar, right? So I have a color bar from 20 to 90 in this way. So I map all the data points with a color instead of a number, and then I paint the plot with the color and see what the plot look like. So first of all, I generate a grid and I snap all the data points into my grid. And based on the value, for example, 31.73, I will get a color that is somewhere close to blue down here. And 88, this one will go way up down here close to yellow. And then based on this, I color each block based on the color specified by the color map here. And I got a plot called a pseudo color for the array, which looks like this. Right? So now you can see that you have a peak down here, you have a minimum here, maximum here, and median values down here immediately based on the color. So that's how we do the pseudo color plot. So before we talk more about it and a couple of concepts, so there's difference between true color, false color, and pseudo color. So true color is the actual color you get from your typical camera, from your phone, for example. And that's what you see with your own eyes. And false color are usually those pictures filtered by some algorithms, right? For example, you have an ultraviolet filter or something, so you get these are called false colors. And pseudo colors are slightly different because they begin with a single band of data, from one single filter. So this means that for each pixel, and you have a choice of colors which is taken from a map. So now I'm mapping a color based on the map value into the map, and that's based on this single color map. I generate a picture with colors based on the values, and that's called pseudo color maps. Right, so there's a difference between these colors. All right, so how to create pseudo color plots for two-dimensional NumPy arrays? So you need two things. One is that you need to know the location of the grid, right? Where are those points I want to paint? And the second one is what are the data associated with that grid locations, which means what color do you want to paint at each locations, right? So how to create two-dimensional grid, which is 2D, also 2D NumPy arrays. So we need to use a function called mesh grid in this way, right? So in this case, I generate two one-dimensional arrays, and these are actually 1D meshes, if you call this. So X is an array from -1 to 1 step by 0.1. Remember that 1.1 is exclusive, right? So Y is from 0 to 1 step by 0.1, right? So now that's a 1D array in the X direction. That's a 1D array in the Y direction. Now I use a function called mesh grid. So np.meshgrid, which takes two one-dimensional arrays, X and Y, and convert it to a two-dimensional mesh. Right? So now let's take a look at the shape. So X and Y, X will be 21 values in the X direction. Y is 11 values in that one based on generated by the arange function. Now XX and YY, both of them are 2D arrays. Now they have 11 elements in the Y direction, which is rows, and 21 values are their columns, right? In this way. So you can see that if you put in two one-dimensional arrays into the mesh grid function, you get a 2D NumPy array contains all the X and Y locations of the grid. And in this example, I'm calling them X, X, and Y, Y. Trying to remember myself, these are two-dimensional arrays. All right, so when we have the two-dimensional arrays, we can use that to see what the array look like based on colors, right? It's the same thing if you remember that we use the plot function. Like if I do plot X and I'm plotting the index versus the value of the X, right? So you can do the same thing here is use the function called pcolor. Pcolor means pseudo color, right? So I do plt.pcolor, which means it's a function of the pyplot, and pcolor XX. So I'm gonna color my two-dimensional array XX based on some default color map. And I set edge color equals to K and line width equals to 0.5. And I change the ticks, change the labels and title. And color bar function gives me what the color bar look like, which is very important, right? So if you look at this pcolor function generates something like this, right? So you can see that the x-axis is the index of the 2D array XX. These are column index, and that the row index have 11 rows and 21 columns, and then each one's colored by a pseudo color bar, which means because it's -1, it's dark blue, and +1, it's yellow. So this is a color bar called viridis, and we'll talk about the color bars later, right? So now if you use the pcolor function with a 2D array, and Python will just tell you how it's distributed as a function of index. All right, so you can take a couple of things noticed here. So one is the mesh grid function. So mesh grid function, again, generates 2D arrays. They're usually used as grids based on 1D NumPy arrays. So basically X is the spatial distribution of points along the horizontal direction, and Y are the points along the vertical direction, right? So if you look at the XX and YY, and you can see that both of them have the same shape, right? So XX varies only along the X direction. So at any Y location, they all vary the same. And Y only varies along the Y direction because that's the grid locations for Y, right? So now based on the mesh, now I used the mesh grid function to generate 2D arrays called XX and YY. So now I can use those to map my data based on the grids, right? For example, if I want to visualize a function, which is a function called z, and that's a function of x and y, and that varies as sine pi x times sine pi y in this way, right? So because numpy, it does element-wise operations. So we know that to create a z function, it's really easy. Just use the sine function by xx times pi times sine yy times pi, right? So remember that xx and YY, they're 2D arrays of locations on the 2D mesh. Now Z is the same array size with X and YY, and value is determined by this equation, right? So now if we do pseudo color, which is do P color, XX, YY, and Z, right? So XX is a 2D array of all the X locations, and YY is the same 2D array with all the Y locations. And Z is basically this function, right? So if you do that, and you can see now I have different colors, right? You have a peak with +1, another peak with -1, because that's the sine function depending on where you are, right? So the syntax to put colors in the two-dimensional grid goes P color, X, Y, and Z. Now here both X, Y, and Z are two-dimensional NumPy arrays with the same size, right? If they're not the same size, then Python will tell you something's not right. All right, so the plots we just showed looked very, large pixels and doesn't look very nice. And then now we can use the same code to generate finer resolution with more grid points, right? So now we changed the step size in the X and Y array. These are 1D arrays from 0.1 to 0.02, right? So now I have about 200 data, 100 data points, and here I have 50 data points. Now I mash the 1D array X and Y to the 2D XX and YY grid, right? So I do the same calculation for Z, and now I'm doing plot XX, YY, and Z, which is a function of the XX and YY. So if you do this, and you can see that the grid becomes much finer. So I have smaller pixels here. It's a much nicer plot in this way, right? So a couple of things to note that now the grid has a 100 times 50 grid points, right? So the default color bar is called Viridis, and it's a very nice linear color bar, and we'll talk about that later. And you can see that in the pcolor function, there's an option called vmin, which is value minimum and value maximum. So that sets the maximum and minimum color based on the value of z. Right? So if you change this maximum minimum values, and these colors will be changed based on how you adjust the color bar in this way. Right? So the color bar function here displays how the color is distributed in the pseudo color map in this way. Right. So now we start to talk about color maps. If you have already noticed that you have options to specify different color maps using these using the Matplotlib color maps. If you click this link and you go to the website and get lots of choices of color bars. Right. For example, these are the sequential color maps called, so which means that you get data change from low to high and color the luminosity or the color of the color map changes about linearly. And also there's another one called divergent color maps, so which is really easy to see. For example, let's take a look. So when everything in the middle it's very light, which is usually uh, white, and then negative side is blue and positive is red. So these are called divergent color maps. And there are also another one called cyclic color map. So it goes from, for example, the twilight, from very light color to dark and come back to light again. And there's another big set of color bars called sequential color bars. So you can see that they all vary on the same color with different intensities. And you can see, for example, this one we used to map the COVID-19 cases, which is ORRD, orange, red. So go from very light orange to dark red in this way. So you can see that color intensity increases as the value goes from low to high. And there's another one called qualitative color maps, basic group colors into different groups, and they're usually used in special cases for data visualization, right? So there's lots of choices of color bars, and there's a couple of rules, and there's no perfect rules of what color bars to choose, but there are a couple of interesting ideas about how do you choose a color bar. For example, let's take a look at that Z function we did, right? So now I plot 4 color maps down here. So one is jet, which is also very similar to a color called rainbow color bar. And this is hot, and you can see that from dark to bright through red. And this one is called blue, white, red, BWR. And you can see that negative is blue, positive red, and 0 is white. And this is something similar, just the red and blue are slightly off the change directions, right? So which one do you think is the most suitable color map for the data Z, which is the function that we looked, right? So there's no fixed answer for this, but my personal choice is that I think the blue, white, red one is the best for this one, right? For example, because the Z function goes from -1 to 1, right? So here you have this color bar showing you that blue is negative, red is positive, and white is 0. So for signed data, I think these divergent color bar works the best, right? This one also works, but it's kind of confusing because usually people will think, this blue is a low value, red is a higher value, but red goes to -1 and blue goes to +1. So that's slightly misleading. And for these ones and jets, it's more colorful, but there's lots of data that's, you can see that lots of green areas that's not very useful. These are just locations like taking up your eyes, getting your attention, but they're not really doing anything. And the hot is the same idea. So the rule I would do is that for signed data, for example, you have both positive and negative values and use something like this. Otherwise, use a more linear color bar. And let's see what are linear color bars, what are not, right? So you can see that these are the variations of a color intensity or the lightness of the color map as a function of the data, right? So the horizontal axis, you can see that, for example, this is gray, and you can see data is small and lowest to minimum to maximum, and then this is an increase in the lightness of the color. So you can see this changes as the data increases. It's almost linear in this way, right? So you can see that most of these sequential color maps, they follow this linear trend. And there's all these ones that follow very linear in the lightness is Viridis, Plasma, and all these things. So that's why the default is that one, because when low data to high data, and then the lightness goes linearly up, right? So now you see the problem of the rainbow color bar here is that you can see that as data go from small to large, and the rainbow color bar actually turns, right? So which means that the lightness, the maximum lightness occurs in the middle, or not even exactly in the middle of the color bar. And as data goes up, and the lightness actually drops. So this can generate misleading results when you're trying to map data using a rainbow or jet color bar, because it does not have a monotonic increasing with the lightness with the data. So the structures can be either hidden or you can generate artificial gradients when they're not related to the data. And it can artificially dividing data to different ones. For example, you can see that in the, for example, this data point and that data point, they have about the same likeness, and then that can be misleading and you can't see it in the map. So let's take a look at example. For example, this is one taken from paper showing the total column density of ozone in the global map. And you can see that this is the original figure from the paper, and you can see that's measured data, right? So there's one light blue curve showing you where the gradients are, right? Because that's a change from a red, orange to green, right? So you see this is a large gradient. Gradient means the rate of changing in color or in the data, right? So this is a very large change in the rainbow color bar, but actually it's not really the case, right? Because if you look at the rainbow color bar, you can have these variations between yellow and green. So there's a boundary down here. But then if you change it to a orange to red, more sequential color bar, and you can see that the maximum gradient is actually not in the subtropical region. It's actually in the subpolar region. Look at this. Right? So that's the actual gradient calculated based on data. And you can see that largest gradient is in the subpolar region, not places indicated here. Right? So that's what's the rainbow color bar is introducing this artificial gradient. Looks like it's an important feature. It is there, but it's not as important as you see in the actual gradient, right? So that's why a sequential color bar or linear color bar works much better than a rainbow color bar in lots of cases, right? So you can see the changes in the real locations, right? So now, next one, let's think about this. Now we can generate 2D color plots and using the pcolor function. And then that gives you a pseudo color map showing you how the data is distributed based on field color, right? But sometimes we want to see more of the lines, contour lines, like the equal potential line, equal height line, all these in the geo map, and you see where those contours. And there's another useful function to visualize these two-dimensional distribution of data is using contours, right? So for example, we do the same mesh grid. So X, Y are 1D arrays along the X grid and Y locate grid from -1 to 1, 1 to 0 to 1. And then we use the mesh grid to make a 2D array called XX and YY. And then I generate Z function, right? So in the last slide, we used the pcolor. Right now let's try to generate contours. So contours, basically, if you do the contour, so the syntax goes plt.contour, the same as X grid, Y grid, and the values, and then you can get a color map in this way. Right? So if you do this, and Python give you these lines, so there's 7 lines. So you can see that each line has a color indicated in the color bar. So you can see exactly what that is, right? For example, this one corresponds to -0.5, and we can see that where that contour is, right? So the syntax of the contour function is contour x, y, z, and plus options. And here both x, y, and z, they have to be two-dimensional arrays. So x, y are usually generated by the mesh grid function, and z is generated by either data or it's a mathematical function. Right? So there are 7 contours, and then that's by default. And we use a color map called red-blue, so which is the divergent color bar, but there's negative is red and positive is blue. And there's another interesting thing is that this is not very useful, right? Because there's not enough information to tell you how the contours are distributed. For this one, it might be okay because it's so regular. Right? So the most important thing you need to plot a contour figure is usually how to set the contour levels. right? So the syntax goes like this. So contour X, Y, and Z, these are 2D arrays, and the levels equals to whatever contour levels you do, right? For example, in this case, we want to set the levels from -1 to 1, but it's actually 0.9. So step by 0.1, so I will have 20 contours using a jet color bar, and then this is what I get, right? So what I did here is I specify the contour levels manually. So you can see that this is minus -1, which is basically a dot, 0.9, 0.8, 0.7, 0.6, and all the way go to the positive value. And then my color map now is jet, which is rainbow, not perfect, right? You can see the 0 contour is exactly in the middle. So another thing we did is called the C label, and you basically label the values of the contour within the contour, right? So C label down there, inline equals to 1, font, change the font, and format. If you still remember how we format floating point numbers, so I want 3 digits, and 2 are after the decimal point. And then you can see that this is basically a contour value. And you can see if I did another trick here is that axis equals equal. So if you do axis equal, so Python will set the aspect ratio to be 1 by 1. So you get, if it's a square grid, and you get exactly a square, right? So also, there's another function when we do the contours, and you can basically fill the contour levels with colors. And then you can have a more continuous gradients of colors, not pixeled, but you can see the variation of the contours, right? So the syntax is contour F, and F means filled contours, right? So everything's the same. You got X, Y, and Z. X, Y, Z are all two-dimensional arrays, have the same size. X and Y are the grids. Z are the values. And levels are how many contour levels you wanna show. So if we do figure equals to plt.contour F, XX, and YY, and Z, that's the same thing. And I said axis, color bar, and also label everything, I got something like this. All right, so you can see I still get 7 contours, but between the contour values, and it's actually fixed, right? So you can kind of see that color maps to something like this, right? So again, default is not so great. And the problem here is that I let Python to choose how many contours and what levels to plot, what color bar to plot for me as default. And that's not usually a good choice to do. So what I need to do is that I need to usually to set levels of contours. So here I want from -1, 1.1, use the in-range function. I use the blue, white, red color bar as the one that my favorite, right? So if you do that, and this is a much nicer plot, and you can see, right? So the negative is blue, positive is red, and you can see these contour levels basically tells you how the data is changing as a function of location, right? So the question, so why there's a hole in the center of the red cell, not here? Think about this. Right? So this has something to do with how you set up the contour levels, right? Here, the in-range function. So 1.0 is excluded, right? So the last contour here with positive value, that will be 0.9. So anything above 0.9, and Python will say, yeah, I'm not dealing with it. So it's showing something like it's empty because the data is higher than 0.9. Right? So if you change this to 1.1, and you will see a filled contour here, and you should play with that. All right, so now let's put everything together. So let's put some two-dimensional data on a map using the contour F or the pcolor function we used. So you'll be using mesh grid to generate a two-dimensional grid, and use the contour F to plot the data, and then you use the map function to generate a map, and then you put everything together, right? So if you still remember how we generate base map projections, so from MPL to toolkits.basemap, import basemap, and then now we're generating a map with a projection called ortho, right? So they're giving a globe, and this is the viewpoint of what the globe looked like. And then this is how I generated coastlines and generated parallel and meridian grades, right? So this is a globe map that generated here, right? So now if you want to plot data onto a map like this, like in earth sciences, right? You're working with data taken from either globally or locally. So mapping data to a map with the topology, it's a useful skill, right? So how to map data on a map? So first of all, you generate a map M with the desired projection in this way. And then we generate or load a longitude latitude grid, right? We need the grid. And the third part, we generate data or we load data onto the grid. So the grid and the data must have the same size. All right, so then we map the longitude, latitude gradient to a map coordinates. If you still remember that whenever you try to plot something, for example, if you remember that we plot the location of the typhoon trajectories or the location of where Hong Kong is. So you need to map the longitude and latitude to the map coordinate. So base map knows where to put those points, right? So now you adjust the scale labels and show the color bar, etc. Right. So let's take a look at this. So we have a data set called eTopo, which is the topology or the height or the elevation of the surface of the Earth, right? So these are the load functions, and you can also use other methods. But here I use the NP load txt function to do it. If you still remember what that is, so elats is a 1D array with 540 latitude bins, and this is a long and skinny array. And elons is a 1D array in the longitude with 1081 longitudinal bins, right? So eTopo is the topology of the Earth with a 2D array with 540 rows and 1081 columns in this way. So eTopo here, which we just loaded, is an elevation for each at each longitude and latitude cell. Right. So in order, so let's see how we're going to map the eTopo values onto the base map global we just generated. Right. So the first thing, we use the mesh grid function to convert lats and longs to a 2D longitude latitude mesh grid. Right. So you've already learned that. So first of all, we create a map, and we already talked about it. And if you don't remember how to do it, go back to the lecture 8 and trying to figure out how we do that. And then we load the longitude, the latitude. And remember that I just used the print function. You know that eTopo is a 2D array, while elons and elats is 1D array, but they have the same size in each dimension, right? So the third one is I'm generating a 2D longitude, latitude grid. Use the mesh grid function. So mesh grid, I put in the 2D arrays of longitude and latitude, a 1D arrays of longitude, latitude, I got 2D arrays XX and YY. So now I map XX and YY onto the map coordinates using the M. Here, M is the name of my map. Right? So by doing this, now you can generate a contour plots using m.contourf, which is very convenient, just slightly different. So what does that mean is that I'm using the map coordinates to generate a contour with filled colors. So X and Y are the mapped geometry, and eTopo, that's the elevation at each location with 30 contours, and I'm using a jet color bar. And if you look at the results, this is what you get. Right? So you can see that what this did is that I just mapped the elevation of the surface of the Earth onto the globe projection. And you can see that's what you get. So there's a couple of levels. One is that these elons, elats, these are 1D latitude, longitude arrays. And then first you convert them to 2D longitude, latitude grids using the mesh grid function. And then the next level is that you need to map those locations. They're geographic longitude, latitudes, and map them to the map coordinates, which is called X and Y. and then use the X and Y in the 2D color plots. So here I use the contour F, and you can actually use pseudo color or other things. All right. So there's another example we're going to look at, and I'm not going to go into too much details at the moment, is that we're going to look at IGRF. And IGRF is the International Geomagnetic Reference Field. If you took the geophysics course and you know what that is, and then that's how we visualize the distribution of the geomagnetic fields, right? So IGRF here, I've prepared a module called MK make IGRF. So MK IGRF, do IGRF. So that's a function that tells you the magnetic field and the declination, inclination at your place with the given time, right? So first of all, what is a magnetic field? And so it's a vector, which means that it has directions and intensity. As you can see that this is basically a dipole field, and this is a more realistic Earth magnetic field, which comes out from the southern hemisphere, goes back to northern hemisphere. So there are a couple of concepts that you have different components. You have the up and down component, east-west component, north-south component, right? So the total field intensity is basically the magnitude of that three components. And there another one's called declination, is actually the deviation of the magnetic field compared to the north. And inclination is actually how much is the field to dip down below the horizon. Right. So if you don't understand that these details, doesn't matter, because that's just the details is not like focus on how to generate maps of magnetic fields using given the IGRF, right? So now let's first use the make IGRF module. So import make IGRF. If you still remember how to import module, so download the module from the Moodle and put the module in the same folder or same directory or folder as your Jupyter Notebook file. And then you can import the module. And Python knows that we're going to look for this module in the same folder. Right? So if you look at help, make igrf.do igrf, so that's the main function. It takes 3 inputs, longitude, latitude, and date, and returns 4 variables, x, y, and z, and f. So there are different components of the magnetic field, and F is the total field intensity, right? So there's another one handy function called make igrf.cart to dir, which calculates the declination, inclination, and the field strength for you, right? For example, if we do putting the latitude and longitude of Hong Kong, and then we call the do IGRF function. And remember how we call a function, we give longitude, latitude, and year 2008. And then I got 4 components of the magnetic field. And now I'm using the cart to dir function to convert the XYZ components of the magnetic field into the declination, inclination, and total intensity. And then I print it out. And you can kind of see that the declination is 357.2 degrees, inclination is 32 degrees, and that's the total field intensity in nanotesla, right? So now we can put things together by using the IGRF module and to map the intensity of the magnetic field into a map, right? So for example, in dates, we wanted year 2008, and longitude is 0, and then we use the mag map function. So the mag map function and gives you the declinations, inclinations, and total B field at longitude and latitude. So that's generating a map. It's a 2D array in this way. So after calling the map function, so we have 3 2D arrays called ds, which is declination, is the inclination, and bs is the magnitude. And together with 2 1D arrays, longitude and latitude. Right, so longs and lats, they're 1D arrays. So remember that how we're gonna map those to a map is that first we create a map with the hammer projection, and we map the longs and lats that's generated by this function and using the mesh grid. So now XX and YY, they're 2D longitude latitude grids, but in geographic coordinates. Now we map the geographic coordinates into the map coordinates called X and Y. And now I'm using the contour F function to plot X and Y and the total intensity of the B field using 30 field contours automatically without specifying levels. So Python is going to do that for myself. And using a color map called JET, right? So we also can add a color bar and put the location at bottom, which use the color bar function. And now we can put everything together, and this is what the total magnetic field intensity distribution on a map, which is quite nice, right? So you can see that this hammer projection is generated by base map, and the data is generated by magmap of IGRF in this way. So, and you can see also that the declination, inclination, and magnetic field on the one, and you can see that you have a maximum intensity in the Antarctica and the lowest in the South America. That's called the South America anomaly. And there are lots of things to do with this. The point here is not the IGRF itself. It's that when you're given something like IGRF, how do you use the code to generate information that's needed? You don't need to be an expert in geomagnetism, but once you are given the data set and you know how to visualize it, how to analyze it. So that's the point of data analysis. All right, so that's pretty fun, right? So let's try to generate some maps and IGRF and creating inclination and declination plots.